3. Yeah, let's put it at 3 for a second. All right, 8.1. All right, so in 8.1, so here we're going to talk about polar graphs real quick. So I'm just going to briefly do a quick overview, or polar coordinates, really. Coordinates, if I could spell today. So polar coordinates come in the form of r and theta, where r is your distance from the origin and theta is your angle. And so here we're going to be doing everything in radians, at least as I have it drawn here. And so here, if we're giving the coordinates of like 2 and then pi over 3, you're just going to go, you're going to start here, you're going to go to pi over 3, and you're going to go 2 units. So here it'd be 1 unit, 2 units, and that's that here. So I come from a physics background, and so a physics background, we don't allow all this, the stuff that kind of what it's been allowed here, because here we allow r to be negative, so I can do -2. Let's do -3, right? I can graph -3 and then say pi over 2. So -3 pi over 2 means I go to pi over 2, instead of going up, I'm going to go down, so I'm going to go 1, 2, 3 units this way. In the physics world, we demand that r be greater than 0. And then we also demand that theta is only between 0 and not including 2 pi. And the reason is then every point besides the origin has a unique coordinate, which leads to it. Here, you can have the book allows you to do multiple things. Like I could have like 2 pi over 3 plus 2 pi as my coordinates, and then I'd go around once, head back to pi, and then go up to 2. Or I could have 2 or -2 plus pi over 3 plus pi. So if I do that, I'm going to be at pi over 3 plus pi is 4 pi over 3, right? So if I go here, it's 4 pi over 3, and then I can go back, and here I'm back at 2. So all these 3 points end up at the same point. And so in physics, we kind of disallow that, but in this book, we allow it. So I'm so used to saying r has to be positive, right? And all this other stuff. Your book gives a lot of other ways of going between these two. So let me open up a new file real quick. New. And so there's ways to go between them. So here, if I want to go from polar to rectangular, I'm going to be using x equals r cosine theta, and y is equal to r sine theta. And then if I want to go from rectangular to polar, I use the following, which would be r squared is equal to x squared plus y squared, and then tangent theta is equal to y over x. Okay. And so you use these two to kind of go from one to another. Because notice here, if I'm in my polar coordinate land, right? Here, if I'm in a polar coordinate and I've gone pi over 3 distance here, and I've gone 2 distance here just to keep it the same, right? Let's go back to here. Notice that the cosine will give me this length, my x, and the sine will give me this length. So here x would equal to 2 cosine pi over 3, and then y would equal to sine of pi over 3, and that will give me my point. But you can use this for equations as well. So here you can write equations as points. So you can convert points over, you can convert equations over, and the one the book gives you is just x squared equals to 4y. So here you just plug in, or where you're seeing x, you just put in r cosine theta squared equals, squared for r sine theta. And then here we have r squared cosine squared equals 4r sine theta. So we can cross off 1r, and we'll just divide out cosine squared. So we have r equals 4 sine theta over cosine squared theta. Let me put the square here. Okay. And so here you can just translate between one and the other. And so there's a whole bunch of ways of doing that, and you kind of go over that. So that's how this is. So the second part, so that's what 8.1 really is about, just going from one to another and then back. We'll do some problems from your homework to help you get through some of it. And yeah, so we'll do some problems from the homework to help you get through some of it. And then we'll go, let me actually do one the other way. So I'm going to do one the other way real quick. So let's pretend we have r equals 2 plus 2 cosine theta. I'll do one of the other ones. And so this looks like this is one of our polar graphs. I don't remember if this is I honestly don't remember the names of the Limicons, the Cartesians, I just graph the things, right? So here we have one of these. So going from here, how do I do this? Well, I just plug in, well, r squared is equal to x squared plus. So what the book has suggested you do is just multiply everything by r. So you get 2r plus 2r cosine theta. Then here, you can just go x squared plus y squared, because that's what r squared is. R cosine theta, we know what that is. So we have 2r, and then we have plus r cosine theta is 2x. All right, and so in order to finish this, we need to get r squared again. So we move everything over. So we have x squared plus y squared equal, or minus 2x is equal to 2r. And then here, we can just square both sides again. And so this ends up being a huge mess, right? But we'll just leave it as the mess it is. And this will be 4r squared. And then the last thing we can do is x squared plus y squared minus 2x equals 4x plus x squared plus y squared. Okay. And so this one's a little bit more complicated. We'll do some of your homework problems of this, and we'll work through how to get to that. Okay. So that's 8.1 in a nutshell. Let's do 8.2. Let me open that up. All right, so let's go back to this. Let's add a new layer. And all right, so let's do 8.2 really fast. Once again, if this is not everything for you, please go ahead to choose George's stuff this week. Some of this is review for you guys, and some of it's not. So graphs of polar. All right, so we're going to start with the two simplest graphs. So here we have a graph of r equals some a, and then theta equals some b, right? So if r equals a, so here if we have r equals like 3, that means we don't know what theta is, so we just say r equals 3. So when theta is 0, we'll go 1, 2, 3 in, so that's here. Let me not do in blue, I guess. Let me do in red. Let me do red. That's what your book does. And so here it'd be 3, here it's 3, here it's 3. Doesn't matter what the angle is. I'm always going to produce a 3. Okay. And so that just goes around. And so here I have just a circle. Oops, if I could if I could draw a circle. So r equals 3. Same thing for r equals 5. We'll just go out 5 units. 1, 2, 3, 4, 5. And here we just draw this circle in. And so r equals some a is a circle, right? This is just a circle. Theta equals some b is a line. And so let me go ahead and let me just make a new layer for that. So let's have theta equals, let's say, pi over 4. So here, it doesn't matter what r is, theta is always pi over 4, and so it's just this line of pi over 4. But it also extends into the negative version, so it would be also 5 pi over 4, so all the way across. Or actually, no. Here, it's just this. Just that. Should be the... No, your book does do that, right? Just double checking. Your book clearly says this is okay because I can have negative r. I'm used to it being a straight line because of my physics training. Please be careful when you work with polar graphs to know which one you're allowing. If you're allowing negative r's, you can have something that looks like this. It's just a complete straight line because you're allowing negative r. If you're not allowing negative r, it's just a ray. By that, I mean it just shoots out in one direction. All right. So let's graph something different real quick. I'll go ahead and do that. I'll just back up. So let's pretend we have something a little bit more standard. So we have like 2 sine of theta. And what your book suggests to do is you just write in theta, and you write in your r, and you just make a little chart, right? When theta is equal to 0, sine is 0, so you get 0, right? When theta is equal to pi over 6, sine is a half, so 2 times a half is 1, right? When pi over 4, you get 2 square root 2 over 2 times 2, which is just square root of 2. Okay. And if you did this and kept on going, you're going to get, let's just keep going. So pi over 2 gives you 2. Let's just give some, we don't need to do all of them. So 2 pi over 3 gives you square root of 3. 3 pi over 4 gives you square root 2. And then 5 pi over 6 gives you 1. And then pi gives you 0. And then here, when we go through the negative ones, it just repeats itself. And so here, I'll start at 0. I go to 1. I go to pi over, oops, hold on right here. This would be 1. Let me zoom on in so I can graph a little easier. All right, so at pi over 4, it's square root of 2. So about here, at pi over 3, it's 2. No, pi over 2, it's 2. Here would be square root of 3. So actually, square root of 2 is here and square root of 3 is here. Sorry, here. And then it just kind of comes back the same way. And if I drew this correctly, it kind of makes a circle. And so that's what the book tells you to do. Is just go ahead and just filter all this out and draw it. George shows you a nice way. George just says, oops, George just says here, oops, hi, why am I on? I grabbed white. George says just graph the thing. And so here we'll have pi, we'll have 2 pi, here's our quarter marks, right? And here we have, it comes up, goes down, goes down, comes up, and then here this is at 2 and minus 2, right? And then use these to get all your data points to do in here. That's also a wonderful method, right? And so here's the 2 methods that we teach you. One, you just plug in points, and honestly, this is what students had to do when we were teaching this, where you couldn't use a calculator whatsoever. But since the pandemic, I think the rules are going to change, right? Well, at least for you guys, everything's online. So let me show you what you guys will probably do. All right, so here we're just going to open up Desmos. So here I've been using Desmos to do all my graphing for all my things. So let's just open this and we'll just use this for everything. So here, so this looks like Cartesian coordinates. Well, how am I going to do that? Well, the first thing you want to do is click this little graph setting, this little wrench right here, click it, and you're going to switch from grid. You're going to see one that looks like this. You're going to see one that, just click the other one. That gives you your polar graph. Okay, so now this looks like a polar graph. Much better looking than mine, right? Much better looking than mine. Second, we're going to type in r equals, and then we're going to hit 2 sine. We're going to put open a parentheses, and you're going to type in theta, theta. Yes, okay. And presto, it draws what we need, okay? And so here, it'll draw it for us. and it does all those calculations, so we don't have to do it by hand. Okay, and so here we can go through all the things that it wants. And so here the book will say, sure, let's do 2 plus cosine 2 cosine theta. So the one graph we just made a little while ago. So remember, theta is theta. It automatically switches it, and so we get this what we call the cardioid, right? Because it looks like a heart, right? It looks like a heart, so that's why it's called a cardioid. Let's see if I can. What's the one that looks like a heart? I think it's 2. Is it 2 minus sign that officially looks like the heart? Yeah, so it looks like a heart, so that's why they call it a cardioid, because it's, boop, boop. That's where the name card, like a cardiac surgeon is a heart surgeon, so cardioid, so it looks like a heart. That's where the name comes from. So you can type those in. You're going to get the flowers if you put in like the 2's here, right? So here, let me get rid of this. So here, if you have a 2, here if it's a 3, you'll have 3 leaves. Here you have a 4. You'll have 8 leaves. Here, if you have a 5, you'll have 5 leaves. And so if it's an odd number, you get that many leaves. So if I type in 7, there'll be 7 leaves. If I type in 9, there'll be 9 leaves, right? If I type in 11, there's 11 leaves. But if I type in even numbers, you get double that amount. So here I get 4 leaves. Here I'll get 8 leaves. Here I'll get 16 leaves. And so for that, it gives it double. Does that make sense? Are we going to have to memorize the shapes or no? No, because let's face it, you guys are always doing this online. You can always type it into Desmos, right? True. So, oh, I have another late friend. Okay. Let me mark my other late friend real quick. What's your last name? But for the future class, should we memorize it? No. All right, so, all right, you guys ready for some dead honesty here? I got a PhD in math. The first time I learned how to do this stuff was when I taught this class. I'm not gonna lie. I was sitting there thinking, wait, do I know how to do this? And I figured it out just by hand. I'm like, yeah, I can do it by hand, but I'm like, why is this part for? Because I mean, the next thing your book literally tells you to do is how to do it all in your graphing calculator, right? And then it gives you, just gives you. Let's go back to it. Yeah, your book literally tells you how to do it in your graphing calculator, and then says, okay, so if I have it to be like 4, it's a graph of 4. If I have it to be 2, it's a graph of 2. So what I would do is just memorize this real quick. So the things that I would memorize is, here we have, so if it's r equal to some a, it's just a circle, right, at that. So even if it's like pi, right, even if it's some really weird thing, right, it's just a circle at 3.14159 on whatever, right? If it's theta, I'm really kind of curious now. Where does your... No, it won't let me do it. Sorry. Okay, so you can't graph the thetas in this one. So the thetas that necessarily you have to do. All right, so it won't allow, so it's only doing R graphs right now. And so if you have theta equal to a sine, let's just make it like 4. 4 sine theta. Theta? Okay. So these are circles, right? And the difference numbers of this, and that's why I wanted to do this on a graph calculator and not do notes, because I can just quickly flip and you can see what's going on. That's what those, there's circles in that direction. If I have a negative sign, it just flipped over on that side, right? So that's what these circles are. And so, yeah, just get a feel for them. And then if it's 2 cosine. All right, so these are spirals. So if you have 2 theta, it's a spiral because it goes out because r will get bigger as your theta goes around and around in circles, right? We can do like 1, gives a real simple spiral. Let's just do 0.2. That's a really heavy spiral, right? And notice it only graphs so much. After that, it didn't care no more. 5. And so these are spirals. And then in here, if I have 4 cosine, these are circles on this side. And if I'm putting negative sign, there's circles on that side. And the 3 just tells how far that circle goes out. So you start at the origin and you go to 1, or you can go to like 7, right? And so that's how you tell these circles. And so graphing these by hand, to me, is less useful than knowing just how these things operate, right? Just how they operate. And so how these things operate in the fact is, and so here we have circles, we have a bunch of circles, and so those are all the circles. And then we did the roses, I showed you all the roses, and the roses just strictly ask how, if it's an even number, you have two leaves for the rose. If it's an odd number, you have 1 leaf. We showed all that. And the only other thing are limicons. Limicons, so here limicons come in the form of 2 plus 3 or 2 cosine theta. And so if these two are the same, we call that cardioid, right? If these two are the same, if they're different, right, like 3, we have these little loops, and we start calling these limicons, right? Or 5, here we have the big loop, or we have 6, we have a different loop. So these are limicons. Unless you're doing really fancy stuff, this is what it is. And so how do you do this? You can do it by hand by either writing them all out or graphing it like George showed you. I think graphing it like George showed you is a nice way of doing it. Writing it all out, just kind of a blunt force, will always work for you, but get used to using Desmos for the polar section, right? Because we'll use that into this other stuff. We'll do notes next time, but let me explain something real quick, which I didn't explain, which I want to explain, is that most of you, 90% of you, actually have a really good sense of what polar coordinates are like. And what do I mean by that? Most of you run off a polar system in your head, and you would think, no, I don't. It's like, yeah, you do. So we have a little house here, right? This is your home, wherever you live, right? Wherever you live, this is your home, right? You have a friend that lives, this way, and he's about, 3 hours away, right? Or maybe like 30 minutes away, right? Maybe not 3 hours, right? And then you have another friend over here. You have school over in this direction, and that takes you, 40 minutes, right? And then you have the store you go to, which is like 5 minutes away, right? And so you put yourself at the center of where you're at, and then as you drive around, so you just think of, instead of distance, you think of time in a car, usually. You may be walking distance. And so you kind of run off a polar system in your head because you use yourself as a center, and then you said, which direction do I go and how long does it take? Instead of distance, it's how long, right? And so polar coordinates tend to be not as esoteric as they seem to be when we teach them, because a lot of people kind of run off a polar system. It's like, where am I at? Where do I need to go? And so hopefully that kind of helps. So that's the whole section in, a half hour? Less than that, right? So is there any questions you'd like me to go from the homework to kind of work through with you guys, or that? So, but for future classes, to answer your question, do you need to memorize these shapes or no? No. If you guys see these outside of this class, I'll be exceedingly surprised, right? Just to be honest. The reason we teach it to you is just so you can get used to manipulating polar stuff before we do other things, okay? You'll see polar coordinates elsewhere. They use them in physics a lot. They use them in other classes a lot. So they exist and they use them. They're really good when distance matter, right? When you're using Cartesian coordinates where position matters,